Hey everybody, first day of chapter 16, our last one. So if you looked at the weekly plan, today is Wednesday and we're just doing one day on chapter 16, and this is actually a review of everything you needed to know from Chem 20, acid-base chem. And then tomorrow you will have your chapter 15 quiz. It's only a quiz this week, no assignment, no written assignment. So today is probably like a 30-minute lesson review of everything you should have learned in Chem 20 and maybe a little bit more. And then tomorrow morning you'll get that chapter 15 quiz. And then next week we start digging into chapter 16, which will take us about, 8-9 days. So early June and we're done. Can you believe it? It's amazing. We're getting close. So hopefully you are still with me, hanging in there. Nice job, all of you, on your last equilibrium assignment. It was very well done by many, many students. It was a joy to mark, even though it took me many hours, but that's okay. That's my concern, not yours. Okay, so let's rock and roll. On the slide, so in your study guide, we are working on page number 315. Yeah, 315. So you guys know about equilibrium constants. This is a new one for you. It's called Kw. And Kw stands for water's ionization constant. It's really quite unusual, but it is possible that two water molecules can collide. And if they do, you can have a transfer of a proton. So a proton will leave one water molecule. If it leaves water, it turns it into hydroxide, and the other one gains it and turns into hydronium. So in a glass of water, you will have water molecules colliding and turning into hydronium and hydroxide. Now, because it's gain X, they're always equal. And that way you don't have a glass of water that's acidic or basic, because the acidic and basic hydronium and hydroxide cancel each other out. So overall, the water is still neutral. And this doesn't happen very often. Less than 1/1,000,000% of all collisions do this, but they do. So at equilibrium, if this reaction is happening in water at SATP, you will get this concentration of hydronium. So what would be your concentration of hydroxide? Correct answer would be the same, because they both gain X, 1.0 times 10 to the minus 17. Now, if you are going to write out the equilibrium expression for water at equilibrium, this is water is a liquid, so they don't have a concentration, so they don't count. So the equilibrium expression is only the products. Concentration H3O plus, concentration hydroxide, and we have those values, 1.0 times 10 to the negative 7 times 1.0 times 10 to the negative 7. So Kw is 1.0 times 10 to the negative 14. And like every other chemical reaction, it is a constant. It does not change at SATP. So at that temperature, the Kw for water is always 1 times 10 to the minus 14. There it is. And that's in your data book as well. So it's a constant we can work with. Now, what makes this constant interesting and useful is because these two multiplied together always equal 1 times 10 to the minus 14. If we increase one of them, what has to happen to the other? It must decrease. If one goes up, the other goes down. They're inversely proportional. And I'm just going to show you that with a simulation. So we have a container of water, pH of 7. So these little dots, the blue and red dots, represent hydroxide for blue, hydronium for red. If I increase hydroxide, what happens to hydronium? Goes down. If I increase hydronium, hydroxide goes down. They are inversely proportional, and they're only equal at a pH of 7, where they are both 1.0 times 10 to the negative 7. Okay? Inversely proportional. One goes up, the other goes down. Okay, so that's the story behind Kw, and that also answers these questions. How do you make a solution basic? You have to have greater than 10 to the negative 7 moles per liter of hydroxide. How do you do that? Dissociate an ionic hydroxide. If you dissociate an ionic hydroxide, you are making hydroxides or increasing their concentration. Option number 2 is remove H+, because as we saw, if we decrease the hydronium, we increase the hydroxide, which is weird. Just by removing hydronium, hydroxide goes up. So there's 2 ways to make a solution basic, and there's 2 ways to make a solution acidic. All right, so that's some theory on Kw. Let's get into the usefulness of it. So what Kw does is it allows us to calculate the concentration of either one of these if you are given one of the 2. So because we know Kw in your data book, it's 1.00 times 10 to the minus 14. If I have one of these, I can solve for the other every time. So let's apply this to an example. 0.15 mole per liter solution of hydrochloric acid, HCl, 0.15 moles per liter, is found to have a hydronium ion concentration of 0.15. Well, that makes sense because in water, it will donate all of its protons to water, 100% of them, and make hydronium and Cl minus. So that means this 0.15, 100% of it becomes hydronium. So what is the concentration of hydroxide? Well, that's where you use Kw. So Kw is 1 times 10 to the minus 14 equals concentration of hydronium times hydroxide, and we have hydronium 0.15. So bring this one over and divide it, and you get the concentration of hydroxide. And I thought I had figured that one out, but apparently I didn't, but you can do that very quickly. So 1.14 divided by 0.15. Actually, I got my calculator right here. 1 times 10 to the minus 14. Clear. 1 second exponent, negative 14 divided by 0.15 is 6.67 times 10 to the negative 14. 6.67 times 10 to the negative 14. 3 sig digs, 2 sig digs, 6.7. Okay, so that's how you can use Kw, convert hydronium to hydroxide or hydroxide to hydronium. Oh, shoot, just didn't scroll down far enough. There it was. Okay, second example. Calculate the amount concentration, or the moles per liter, of hydronium ions in 0.25 mole per liter barium hydroxide. This one's a little tricky because barium hydroxide is BaOH2. So when it dissociates, we get 2 hydroxides. So 0.25 mole per liter BaOH2 gives us, this is stoichiometry, 2 hydroxides for every 1 BaOH2. So I guess I should have put at the start of the concentration of hydroxide is 0.50. So it doubles. One of those become 2 of those. So now that I know hydroxide, I can figure out hydronium using Kw, 1.00 times 10 to the minus 14 divided by concentration of hydroxide equals concentration of hydronium, which will be 2 times 10 to the minus 14. There it is. Got smart this time and I scrolled down. Okay, so this is stuff that you probably learned in Chem 20. You're probably thinking, no, I didn't. I think you just forgot. It's been a little while. Okay, last one, then we'll jump into pOH calculations. So this one's got a few more steps to it. Determine the hydronium ion concentration and the hydroxide ion amount concentration. So we're looking for moles per liter for both of those. We have 500 milliliters, which is the same as 0.500 liters of an aqueous solution containing 2.6 grams of sodium hydroxide. Sodium hydroxide, 2.6 grams. Okay, well, we're looking for concentration in moles per liter, and we've got grams, so we're going to need molar mass. Molar mass of NaOH, I've already figured it out, is 40.00 grams per mole. So let's get concentration of NaOH first. Concentration of NaOH, moles per liter. So there's our moles. So we flip it. Moles over 40.00 grams. We can get rid of our grams with that 2.6 grams. Okay, so now I have moles, and I want moles per liter. It's half of a liter, 0.500 liters. That goes on the bottom so that we get moles per liter. So when you do the math on that, that becomes 0.13 moles per liter of NaOH. Now NaOH dissociates in a 1-to-1 ratio, Na plus OH minus. So 0.13 molar, 100% high solubility becomes 0.13 molar hydroxide. Okay, well, there's our concentration of hydroxide. Concentration of hydronium, we're going to use Kw, 1.00 times 10 to the minus 14 divided by 0.13 gives us that value. All right, so that's one of our two things today, understanding where Kw comes from and understanding how to use it to convert hydronium to hydroxide or hydroxide to hydronium. How's everybody doing on that topic? Getting pretty good at drawing those squiggly-haired smiley faces. Okay, if you want to practice these, there's 6 questions that you can do in your, 5 questions. Do not do number 6. 5 questions in your textbook. I don't have my text here, so I'm not sure which page they're on, but they're right near the start of chapter 16. So they're a good little review. It'll only take you about 7 minutes and 33 seconds to go through those. All right. Second half of the lesson is pH scale, calculating pH, pOH. So a little review for you. pH scale, the traditional one goes from 0 to 14. You learned that in Chem 20. And you may have learned that it actually goes higher. It goes almost to 16, and it goes down to -1, almost down to -2. Now we have the pH scale, and we also have the pOH scale, which measures the power of hydroxide. And you will notice that pH plus pOH always adds up to 14. So 3 and 11, 14. pH of 6, pOH of 8, 14. You will also remember that this scale is logarithmic, and it's log to the base 10, which means every 1 pH unit is a 10 times decrease in hydronium. So if I go from a pH of 3 to 4, it is 10 times less acidic. 4 to 5, 10 times. 5 to 6, 10 times. What if I go from 3 to 6? Is that 30 times or 1,000? And the correct answer would be 1,000 times. You multiply, okay? It's logs multiplied. So 10 times decrease for each step up, 1,000 times for 3 steps up, 1,000,000 times for 6 steps up. All right, so here are the formulas we're going to use. You've seen these before. I'm going to roll through them quick. The only thing that's going to mess you up a little bit is those special sig-dig rules for pH, pOH. So a reminder, sig-dig rules, you only count the numbers after the decimal for pH and pOH. So I'm underlining them in these examples. 2, 1 sig-dig, 2, 2, 2, any more? Ooh, 3 sig-digs, okay, and we stop there because those are the end of the pH and pOH numbers. 3. Okay, So really quick and easy. Formula, pH. We want to calculate concentration of hydronium. So concentration of hydronium is 10 to the negative pH. On your calculator, if you've forgotten how to do that, you do second log button, which has the 10 to the x. So to the left of the 7 is the log. So when you hit second log, you get the 10 to the x, and we were going to go 10 to the, and that's negative pH. So it was a pH of 6, 10 to the negative 6. Enter. Oh, I did 66. Let's try that again. Second log negative 6. Enter. 1 times 10 to the negative 6. So in my calculator, negative, 10 to the negative 6 becomes 1.0 times 10 to the negative 6. Okay, second one. What is concentration of hydronium with a pH 3.4? So we're going to go 10 to the negative 3.4. Or on your calculator, you're going to hit second log negative 3.4. And you get 3.98 times 10 to the negative 4. 3.98 times 10 to the negative 4. And that is 3.98 times 10 to the negative 4. Okay, sig digs. In our pH unit, there's only one decimal place, so I have to shrink this down to one number. So it becomes 4 times 10 to the negative 4, 1 sig dig. This is a concentration, so it's normal sig digs. This answer is also a concentration, so it's normal sig digs. Okay, try this next one in your calculator. 10 to the negative 11.05. And you get 8.9 times 10 to the negative 12 for your concentration. 2 decimal places, 2 sig digs, 2 sig digs. So we're good to go. Okay, so now we're going to do some hydroxide and pOH. Basically, it's the same formula. To calculate concentration of hydroxide, you go 10 to the negative pOH. So in this example, 10 to the negative 6 in your calculator is 1.0 times 10 to the negative 6, 2 sig digs, because that's concentration. Okay, this one also has 2 decimal places, 2 sig digs, 10 to the negative 12.25 equals 5.6 times 10 to the negative 13. That's a concentration, normal sig dig rules, 2 sig digs. Okay, last one, 10 to the negative 2.250 equals 5.62 times 10 to the negative 13. 3 decimal places, 3 sig digs, 5.62. Okay, so that's the one set of formulas. And the second one, if you're trying to solve for pH, you go negative log of the concentration of hydronium. So in this example, negative log 5.6. And so it's that same button on your calculator. So I would go negative, hit the log button beside the 7. And what was it, 5.6? I forgot. And yes, it was. So negative 0.748. Negative 0.748. Okay, this is a normal number, normal concentration, 3 sig digs, so I need 3 decimal places. So that is the correct answer. With, it's up here, sorry, 5.6 molar is 2 digits, 2 decimal places. So that becomes negative 0.75. Let's get rid of that one from that spot. Okay, I want you guys to do the next one. Pause and try it on your own. Negative log 1.20 times 10 to the negative 16 and you get 15.921. 3 sig digs, 3 decimal places. So I did these two examples on purpose because they're unusual. Here is a pH of negative, and here is a pH exceeding 14. So I told you the pH scale goes from -2 all the way up to 16. So there's nothing crazy about minus 0.75 or 15.921. Those are both within the realms of that pH scale. Okay, last one. What is the pOH? So you're going to go negative log concentration of hydroxide to get pOH. And this is a normal number, 2 sig digs, 5.5 times 10 to the minus 4. And that gives us 3.26. And that's a pOH unit, so it's 2 decimal places to match our 2 sig digs. So those decimal places are all correct. Okay, there they are, nice and neat. How about that? So there's all the correct answers with correct sig digs that I just showed you. Okay, moving on. This is a summary of the derivation of this formula. pH plus pOH equals 14, and it's just using log rules. If you're interested in it, great, you can take a look at that. And if you're not, that's fine as well. You just need to know that to convert one to the other, you subtract 14. So if I told you that the pH was 8.3, pOH is 14 minus 8.3, 5.7. And we always go with decimal place rule. 1 decimal place, 1 decimal place. Okay. All right, let's try a few more holistic examples here where you do a little bit more. So we've got concentration of hydronium. We need to find out pH and pOH. So since it's hydronium, I would do pH first. pH is negative log of concentration of hydronium, 4.2, times 10 to the negative 6, which works out to be 5.38. Okay, sig digs. 2 digits in that normal concentration, 2 decimal places in my pH. Okay, to get pOH, 14, and we usually use 2 decimal places on that one, minus 5.38. So 2 decimal minus 2 decimal places gives us 8.62, 2 decimal places for pOH. All right, I would like you guys to try these ones. Answers are provided. So you can check to see if you're getting them right. Remember that for this one, 0.25 moles per liter of HCl is a strong acid. So it will go 100% into hydronium and chloride ions. So 0.25 molar HCl becomes 0.25 molar hydronium. Okay, so those you can do on your own. You don't need to sit and watch me do those. Simple calculations, correct sig digs are there, and that takes us to an end. This is a summary of all the formulas that we used today. Okay, you need to remember them. They are not provided for you. And then to practice, there's a page in your study guide called KWPH-POH. You did it in Chem 20, but you could do it again. And there's some questions in your textbook. Answers are in the back. And I will put this one in Google Classroom for you to double check to make sure you're getting them right. Then tomorrow is your chapter 15 assignment or quiz. And then on Monday, we launch into chapter 16 acid base. And the assumption is that you will be able to do all those pH, pOH calculations, concentration hydroxide, concentration hydronium. Okay. 2 thumbs up. That's a wrap. Okay. Have a good afternoon, everybody.